Hi, and welcome to this part 4 of our V-block project video. Today we're going to be completing the second groove on our small block and both grooves on our large block with two different techniques. Maybe even three. We'll see. But before that, I've received many questions, but there's two questions that I think I should answer here because they relate to what we're doing. So let's head over to the whiteboard and take a look at those questions. Okay, well here we have three examples, and there's going to be a fourth one down here, but I'm too lazy to draw it. And in the first example here, well, we have a piece of flat stock that I'm going to mill a groove into, and you can see that in red, and here's the groove in the side view. Now we have our end mill seen from the top, and we have a clockwise rotation. It's a clockwise cutting end mill. And we're coming in to the part full width, so it's a 180 degree cut. We're cutting on 180 degrees of the tool's rotation, which is as much as you can get out of an end mill. And the question I received was, wouldn't this be problematic because we're conventional milling on one side of the groove and climb milling on the other? And we would tend to think that that is the case, but it isn't really a problem. I mean, it can be, and we'll look at some situations. But as a general rule, or not even a general, as a rule, we know that the conventional milling, what's going on down here, mushes the part at the start of the cut and needs a lot more pressure to lift up that chip. Whereas the climb milling side of that groove, well, it's getting as nice a cut as possible with very little deformation. And that means that there's a lot less pressure required to cut the climb milling side than there is to cut the conventional side. And that means that the forces don't even out. I have a bit of force in this direction and a bit of force in that direction. If I create a vector or average out those forces, I'll get with the black arrow here an indication that there is a force in this direction and in that direction, so slightly towards this end of the part, or if you prefer, slightly against the feed. Now when I have a force applied against the feed, I eliminate the backlash, and that is what conventional milling is all about. So even though this isn't as conventional as you'd like, because you lose some of the counteraction force here to the climb milling side, it still averages out to something that is quite conventional milling. And that is not the problem here. What the problem here is getting a proper groove. And I know a lot of people think that they're going to get a 1-inch groove with a 1-inch cutter. I guess in a perfect world you would, but this isn't a perfect world. And just take a look at me to figure that out. But if it were, fine, but it isn't. This tool, and we've just mentioned, applies more force on the conventional milling side of its 180 degree cut than it does on the climb milling side. And that means that this tool is going to push against the part much more in that direction than in that direction. It's going to want to push the part away. And that is going to push the tool away from this side. And we're going to get tool deflection. And that means that, well, the groove will not be the size that we want it to be. So that deflection will enlarge the backside and will not affect that much the conventional side. So we're going to get an oversized groove that isn't centered where we want it to be. And that's why when we're cutting our grooves here, I've troughed out the center. I've taken all that material away in one foul swoop, well, several cuts of one foul swoop, a 180 degree cut. And then I'm coming to finish the edges off, reducing this problem. I'll be able to center it one edge at a time exactly where I want it and not worry about tool deflection that much. And there's another thing that needs to be said about this first example, and that is that I can use a 2-flute end mill here. And if it's a small slot, you want to use a 2-flute end mill. Now, there's something very bizarre here with end mills and the grooves in them. The grooves are there to stock chips. Now, if I'm cutting on a 180-degree cut, I want room to stock chips in because I don't want the chips to be rubbing against the part that I'm trying to cut. So I need room there. And the problem with having room is the smaller the cutter is, the less room that I have between the cutting lips in relation to its diameter. And why is that? Well, a groove is a space, is a volume, okay? And volumes get bigger to the 3rd power. So that means that if I go from a small end mill to a slightly larger end mill, the diameter will increase by X amount. The cross-section of the area occupied by the grooves, well, will get larger at the X amount squared, and the volume that can occupy is going to be cubed. So that means that the space between the teeth gets bigger a lot quicker as you get your end mills larger. So if you're using a relatively small end mill, a 1/2 inch or something like that, you really want to use a 2-flute end mill here so that you get more space between the teeth. And you can get away with that here because the tool engages and disengages about at the same time. And that means that as one tooth is coming out, the other tooth on the opposing tooth is coming in. And that sort of makes for a quite stable cut. Fine, so that's pretty well what we had to say about this first example. What are these 2 other ones? Well, they're variations on that. Now, we're not grooving here, we're surfacing a part. So I have a relatively thin bar, and I'm going to be surfacing that side of the bar. I have my cutter in rotation. I've chosen a slightly larger cutter because that will scallop my surface less if I have any head alignment issues. So we tend to use larger cutters for this type of operation. And that's good, fine, but it comes with a problem. First, note that I say here 4 flutes okay, but. Now this would be an application for a 4-flute rather than a 2 because I have a relatively thin part and I have a cut that is quite perpendicular because in this example the part is right on the center of rotation of that tool. You can see here. Well, that means that my force is really perpendicular to the axis of feed. And that's acceptable. I don't like it. It doesn't feel good when you're cutting. It feels a little on the loosey side, but anyways, it's acceptable. But I don't want a 2-flute because that means that my tooth will be coming into the cut, cutting, exiting the other side before the next tooth comes in to do its job. And that's going to be load, unload, load, unload. And that means that I'm going to have a tool that is vibrating and springing all over the place. And I'm going to get a terrible surface finish out of that. I want to maintain a pressure on the tool to limit its jerkiness, if we can say. So in this case, if I use a 4-flute, well, I have more teeth. So when one exits, the other will be coming in to do its job at one condition, that the width of the part is equal or better to be slightly greater than the distance between 2 tips or 2 adjacent teeth on the cutter. And if that's the case and I can cut this way, well, I get a cut coming in, leaving, and just as it leaves, another one comes in, so on and so forth, maintaining a load on the cutter and giving me a lot better finish. But you can't always get away with this because sometimes the part is just too thin. Well, there's something that you can do. We can use a 4-flute cutter in this last example, but look what I've done here. I've offset the center of rotation of the cutter so that it is above the center of the part quite a bit. So that means that this side of the cutter comes in just lower than tangent, and it introduces itself to the part just at a very steep angle. and it will exit the part almost vertically if we keep these sizes in mind here. Now what does that mean? Well, that applies the force differently, and it does it two ways. First, it gives me a little end thrust here that counteracts the advance or the motion of the feed. And that means that really conventional or looseness in the lead screw is not going to be a problem with this example. And what it does also is it lengthens the amount of engagement of the tool. And that means that even if the part is too thin to be a little greater than the distance that separates two teeth on my 4-flute end mill, well, by lengthening the engagement, by changing the center height, well, I can't get around that problem because I'll always have a tooth engaged here. So this is a way to get around this kind of problem. Now I said I wasn't going to draw the fourth example because I'm lazy. Well, it's because the fourth example is the same as the third. It's just that if I offset the center in the other direction, well, I would be mostly climb milling, and my force would be in the same direction as the feed, and I would be running after a big problem there. Okay, and I'd find it too. So I hope this answers the question, and I will see how things pan out, but I'll be re-mentioning a lot of this as we're working on the mill. Now, the other question that I received was that does conventional milling, the one that applies more force, produce less of a burr, and thusly might be better for working to lines visually because you'll be able to see your line better? And the answer there is no. It really, Klein milling applies less force and lifts a much smaller burr than conventional milling, as I mentioned, that mushes the part at the start and creates quite a burr. Really, the only advantage, and there are two, I should say, advantages to conventional milling, is that it is a safe way of working, and the Lord knows that is important in the home shop because our machines aren't equipped for Klein milling. So one advantage. The only other real advantage of conventional milling is that when you're milling the face of a crusty part, let's say a cold roll or a hot rolled steel, well, you can get your cutter to enter underneath the crust and exit through the crust from the underneath. And that is a lot less injurious to the tool. Now, if you are Klein milling on a crusty surface, well, your tool is banging in to that carbide-like surface, that crust, and it can really wear down your cutter quickly. Those are the only two advantages. All the other advantages, well, they go to Klein milling, but it is dangerous, so stick to conventional for now. Now, that's our questions. We have work to do. Now, the milling machine is set up. I haven't removed my cutter. My vise is still aligned, and we have a groove to complete on the other side of the block that we grooved last time. So let's get to it. Okay, so I have my part in the vise here as it was set up at the end of the last video. And that means that the groove that we're looking at here at the top, well, is the one that's already finished. We finished it by eye. Now the reason why my block is set up like that is because I'm going to want to get the block on the other side, or the groove on the other side, to the proper depth. And the other side I'm going to be doing by measurement, so I'm going to want to be a little more accurate. And I can, especially on this mill that doesn't have a good vertical axis, I can make my life a lot easier. Now I cut that groove by eye, and that includes the depth. But I've measured the depth and come to the conclusion that it's 5/1000ths of an inch deeper than the required dimension, which is fine because I still have a couple of thou to take off the side, and I have a plus or minus 5 thou tolerance on that dimension. So I'm well within my tolerance. But I can use that knowledge to help me set up the machine. And for that, I'm going to use a 5/1000ths of an inch shim stock. Now, I know that the bottom of my groove is 5 thou too low. I'm just going to come and touch off this 5/1000 shim stock between the tool and the groove, and that'll position my tool at 5 thou above the bottom of the groove as it sits now. And then when I turn my block over to do the other side, well, I'll have the proper depth. And what's nice here is that this smaller block and the larger block that will follow later, well, they are all the same width. They come from the same bar. So that means that if I set the groove properly now, well, it'll be the same depth for all my blocks, and I won't have to be fidgeting with this. That is one of the reasons why I roughed them all out ahead of time, because now I can set up for my final cut in depth, even for all the grooves. It really saved me a lot of time. Now, I'm going to touch off here, but with the spindle stationary, right? You don't want us to be using shim stock with a tool that's in rotation. So we'll do that, and then we'll be ready to start. But not really. There's one thing that's left to do before we start the touch off here, and that is to go and get our safety glasses and to plant them firmly on our noses. Okay, so my depth is set. What do I want to do now? Well, I've returned to the original side of the block. Now I'm going to come and touch off this side of the groove, so my side of the groove, and take a light cut. Why do I want to do that? I've already cut it once and I'm not up to my line yet. Well, I'm going to want to do that so that I'm sure that my backlash is on the proper side. I want to be coming towards me here on the part, so pushing the table away, in other words, and I want the backlash to not be a problem. I want it on this side. So I'm going to take a light cut, set my graduated collar to 0 on my cross slide, because I'll know where I am then. Take a measurement on my part to know how much is left to come off. Return to this side for a second cut, because I want to cut in a conventional style, not climb milling. Advance the amount that I've calculated and take that final cut to finish this side of the groove. Then I'm going to do basically the same thing on the other side. I'm going to move over to the other side, and in the different direction, because I'm still going to be conventional milling, take a light cut on the other side. Well, what's different here is I'll be measuring the width of the groove here. I want the groove to be 1 inch, so I'll be measuring the width to see what needs to be taken off of the other side of the groove to get my 1 inch width. Once I figured that out, well, I'll put my graduated collar to 0 again and move the required amount to finish that second side of the groove, and voila, this groove will be complete. there. The grooves on the smaller of the two blocks that we're producing, well, are complete. Now, we can clean this up, head over, get the larger block, come and set it up, and start cutting our grooves. Remember, our depth is already set, so don't change anything depth-wise as far as the machine goes. But we are going to be cutting those other grooves with a little differently. It's going to be the same tool and everything, but we're going to do it by edge finding by numbers. And we're going to edge find it two ways. I think we'll do the first one with a touch-off method, and the second side, well, we'll do with an edge finder or a wiggler. It's really an edge finder. So let's clean up and take a look at the grooves on that other block. Okay, so my part is set up and I'm ready to go, but in height, I have nothing to do. I mean, I've already set up the height of the machine on the last part, and this part being the same width, well, the depth of this groove is going to be the same. So that's easy. But after I trough out the center to get the depth finished, I'm going to come around the part on the outside of it without changing my height and come and touch off the bottom of the part with the tool in rotation. I'm just barely going to come and nick the part, and that will indicate to me that this side of the tool, or the back side of the tool, is even with the bottom side of the part. It gives me something, a reference. Once I'm there, I'm going to set my collar to 0, back off of the part without moving the cross axis, and move one whole width of my cutter. My cutter is a 3/4 of an inch cutter, so I'm going to move 3/4 of an inch. That's going to position this side, okay, the front side of the cutter, even with the bottom side of the part. And that is going to be my 0. So I'll reset my collar to 0 there, and then all I have to do, well, is move the amount that I want as far as the thickness of that bottom goes to lead up to the bottom side of the groove. And we want it at 414 thou. We left that 14 thou on the bottom of the part for finishing. And I can take my cut, and that means that this side of the groove will be complete. And when I'm done my cut, I'll be on this side of the part here. So I can then just move over the requirement to finish my groove to its proper width. Now, I want this groove to be 1 inch. I've just finished the bottom edge of the groove. My tool is 3/4 of an inch. So that means that I have to move another 250 thousandths of an inch to get to that top edge of the groove. And that's what I'll do. So best, easiest would just be to re-zero your cross axis, move 250 thou, and come and cut that top side or the other side of the groove. And then this part, or not this part, but this side of this part will be complete. Now some of you are saying, yeah, but you're touching off the bottom of the part with your tool in rotation and you're going to leave a mark. And true enough, I am. But in this case, it's really not important. We left 14 thousandths of an inch on the bottom of the part for finishing. So if I leave a nick there, it will be erased in the grinding operations. So let's get to it. There, that groove is complete. Now, I want to do the other side with using the edge finder to find my zero. But there's a problem with that. I'm going to have to pull the tool out of the machine to do that. So I don't want to lose my depth. So what I'm going to do is pull the part, deburr it, set it back into the machine, and groove or cut the depth of the second groove before I have to move the head height-wise. And that way it'll be easier to come back to the proper depth on the second groove here. But I'm not going to show that because it's just more of the same. So we'll get back together in just a few seconds when we're going to be doing the edge finding of the bottom of the part with an edge finder. So I've milled the bottom of that groove and it's complete, and all I have to do now is finish the two sides of the grooves. And I want to edge find the part, and here is my edge finder. Now I've pulled the tool out and I've replaced my 3/4 of an inch C5 collet, or R8, sorry about that, 3/4 of an inch R8 collet with a 3/8 of an inch R8 collet, because my edge finder here uses a 3/8 collet to hold it into the machine. Now I could use this with a drill chuck as well, but that would require moving the head, and this collet will just permit me to move the Z-axis a little bit, a lot easier for me. Now we can see that the end of the tool is aligned with the bottom of the part. So the axis of rotation and the bottom of the part are at the same place in the transverse axis, or the cross axis. So the center axis of the machine is above the bottom of my part. Great. And my dial is set at 0. My backlash is on this side. Great, that's the side or the direction I'm moving in, and that's okay, that's what I want. But that is not where I want to be. I want to be above the lower edge of my groove. That's what I want to cut at this point. So I'm going to have to move that 414 thou to get to that point. But that's a problem, because when I move 414, that'll place the center axis, or the axis of rotation, above that surface. And that's not what I want. I want the edge of the tool above that surface. So I'll be moving 414 thou plus half the diameter of my cutter. My cutter is 3/4, so half the diameter is 3/8, or 375. So 414 plus 375 should give 400 plus 300, 4, 5, 6, 789 thousandths of an inch. And that is where I will go to cut that surface. Once I've done that, well, I'm going to do exactly what I did on the other side. I know where I am. I'll reset myself to 0, move over 1/4 of an inch, because my tool is 3/4. 1/4 will give me a width of slot here, or groove, of 1 inch. So let's take a look at that. See you back when we're done machining. There, so that groove is complete, and all my grooves are complete. So we can move on to our next operations. But before we do that, I think it'd be important to say that edge finding is a crucial part of what we do on milling machines. Because if you don't know where you're starting from, it's difficult to know where you're going to end up. And especially if you're using digital readouts, well, edge finding becomes a very interesting and important way of working. Now, I haven't explained much about edge finding. We've seen a few different techniques quickly here, but I do have a video that specifically covers edge finding, many different techniques. So, if you have the time or want to, go Google this video. Now, you can search for it on YouTube, you can Google the title. I don't put links in the videos anymore because links get broken, they don't work anymore, they don't work on all different kinds of machines, or systems I should say, and more importantly, a lot of people just don't like clicking on links, and I understand there are security problems with that. So Google it, search for it on YouTube, or go see it on my webpage, THATLAZYMACHINIST.com. Now, I'm way past my half hour, and we haven't gotten around to drilling and tapping any holes. So that's what we'll be doing in our next video, I promise. So until then, have fun, be safe, and happy machining.